Welcome, folks, to a virtual tour of outer space. My name's Josh. I'm part of the Morrison Planetarium team at the California Academy of Sciences, and it is my very special privilege to be broadcasting out into the internet and hopefully to your homes. We are here, like I said before, for one of our weekly programs called Virtual Tour of Outer Space, where I get to be the pilot, but you, the viewer, really get to be our spaceship captain and decide where we're heading. If you have some place in the solar system or beyond that you would like to visit or know more about, just let us know in the comments. We'll do our very best to pilot us out there. Now, we're able to show you this super cool view using the OpenSpace software. OpenSpace is a really cool planetarium software that also works on your home computer. I'm at my home, broadcasting to your home, and if you've got a computer you feel like would be pretty good at running a simulation of the entire universe, I'd encourage you to download it. The OpenSpaceProject.com is where you can get your own copy of this super cool software and do basically the same tour I'm about to give. We encourage you to check it out. We've actually got an opportunity for you to tell us what you think of OpenSpace at the very end of the broadcast. We'll include a URL for you to tell us what you think of this program and the OpenSpace software as a whole. Now, right now, we are using OpenSpace to look at a very cool thing in our solar system. This is, of course, Jupiter. Now, I like to make people guess which object we're looking at the very beginning, but it doesn't work with Jupiter. It's just too iconic looking. You've got beautiful variation on the surface, what we call the clouds into zones and bands. Zones are lighter, bands are darker. You can see some of that beautiful variation here. If you look at the polar regions especially, you can see wonderful contrast. The Juno mission has been giving us gorgeous insight into the clouds of Jupiter and how they change and the wonderful complexity we see there. So I'm going to dive into some of these bands, and as I do, you get to see that interplay. Like I said, milk and coffee, that swirling effect, that change between lights and darks, and every shade in between. You can see Jupiter's most iconic feature right up here. That is the Great Red Spot, or the Eye of Jupiter. It's a beautiful feature. Gigantic swirling storm with complex layers and geometry all its own. That dark kind of umbral nucleus way down there in the middle makes a tiny dot like a pupil inside the eye. But if you're looking for a face on Jupiter, you really can do no better than this one floating around up here, Jupy McJove face, it's sometimes called, or Jovie McJove face. But this is a weird looking monster face that's popped up in some of the belts of Jupiter that was captured by our, I think, Hubble imagery as they took a mosaic of multiple images across the surface of Jupiter. It's super cool looking. If you have the opportunity, you really should check it out. Hubble has some wonderful shots of Jupiter. When you combine them with the amazing shots we get from Juno, you get a holistic understanding of the surface of Jupiter as it is now, but it's always changing. Unless we left a mission there in perpetuity, we would never capture all the cool stuff that's going on Jupiter. And turns out cool stuff isn't just happening on Jupiter, it's happening around Jupiter too. Jupiter has 4 of the biggest moons in our solar system, including the 4 we call the Galilean moons. Now, I'm taking you to one of those Galilean moons, I think one of the smallest ones, and the closest of the 4 to Jupiter. This is Io, or Io, if you're a classics major. When you look at it up close, you can see some interesting variation on the surface. I've heard it compared to a pizza by some. Kind of does look like a pizza, maybe a moldy pizza. You can see yellows, reds, whites, oranges, dark colors, light colors, a whole lot of variation. This is a volcanic moon, a wonderfully active place with a huge amount of volcanoes going off pretty much constantly. Now, when we look at Io, you might ask yourself, well, how is this little object, and it is very small, smaller than our moon, so active? Small objects like the moon, even Mars, have cooled off over the age of the solar system, lost their activity. Larger objects like Earth have a little bit more activity going on. There's even some suggestion that Venus might have some level of surface activity. But a small object, by all intents and purposes, should have cooled down over time and become just a ball of rock. The secret of Io's activity is Jupiter itself. Now, there's tidal forces pulling on Io over time, and every pull imparts some energy. And energy is easily translated to heat, and that heat keeps activity going. Or at least that's what we've been considering for a very long time. Turns out there's a recent publication, I think Bing, our producer, can drop a link in our comments for you to check it out, that suggests there could be another mechanism for heating. It is still tidal, but the energy isn't coming from Jupiter. As huge as Jupiter is, it's all too easy to assume that the activity of the Jupiter system is entirely sort of the fault lays with Jupiter. Look how big it is compared to anything else around it. But actually, these moons are all relatively large. And by neglecting the influence they might have on each other, maybe we're oversimplifying the problem. That's a problem physicists run into sometimes. It's so much easier to do the math when you drop out some of the variables, but by ignoring those variables, sometimes you fail to see the whole picture. So we've seen this tidal force interacting on several of these Jovian moons, and that interaction imparts energy to all of them, making this a complex and interesting system. Think about the tidal play of one moon on another. Here on Earth, we get a huge amount of influence from our moon. It causes our oceanic tides, even lake tides in some of the bigger lakes here on planet Earth. Well, there's a lake underneath Europa's surface. That's the moon we're looking at now. I really shouldn't call it a lake. That's a misnomer. It's an ocean. By any measure, it would be an ocean. It's gigantic. And all that water seems to experience some motion, some changing in angle from those other moons. And that motion, that energy imparted to it, is likely part of what's keeping it liquid inside. Now, exploring those subsurface oceans would be an incredibly exciting thing to do, and one humans are actually planning on doing. Provided NASA's slate of missions all become successful, then we will have an explorer orbiting Jupiter and doing incredibly close dives towards Europa to give us as much information as it's possible to get from space about what's going on inside Europa. Maybe one day paving the way for a mission to go inside Europa and do some subsurface exploring. But I have talked entirely too much about our Galilean moons. If there's another place in the solar system you would like to check out, please let me know. The most fun tours are always ones where guests or viewers are suggesting awesome places for us to visit. Now, I've been talking a lot about Jupiter. I'm going to do one last thing about Jupiter before we head elsewhere. We actually have a conversation on Friday where I get to meet with a friend of mine, Eileen Gonzalez, who's going to be telling us about brown dwarfs. Brown dwarfs have a lot in common with Jupiter, and to find out more, tune in this Friday. We are looking at our other solar system gas giant here, checking out the really cool surface of Saturn and its icy rings. Now, looking around here, you can see that cool structure, but we're seeing the rings of Saturn as ice particles by the light bouncing off of them. I see in our comments, Cheryl has a cool idea about checking out things in the universe in other wavelengths. Well, looking at Saturn in infrared, you get to see some of those surface features pop out really beautifully, but I want to do you one better. This is a virtual tour of outer space. We don't always have to just hold to the solar system, even though that's our neighborhood, the part of the universe that people are most comfortable with. But let's check out our more macroscopic neighborhood. Looking around here, you might be able to notice this line-like structure stretching across our view. This is our Milky Way. Now, the Milky Way is gorgeous to look at. Unfortunately, in San Francisco, even when we get a nice clear night, our light pollution is just so significant we don't really get to pick it out. But if you can pick it out, you can often get structures like this, especially in our summer skies, the center of the Milky Way. Now, from a really dark place in our sky, you might be able to pick out the center bulge. And when you do, it is something exceptionally cool. Now, we have a little interface here that allows us to explore some of what's going on inside the OpenSpace software. And by going into our Milky Way, I can potentially... No, we took it off for this. But in our default version that is not focused on just the solar system, you can click a button called H alpha. It shows you the Milky Way in a completely different color. And when you do that, it'll look like a reddish gold blur across the sky. But what you'll notice is how much bigger it gets. There are edges to that blur that stretch out many, many degrees from every part of the galaxy. What you're seeing is the cool gas and dust. To our eyes, gas and dust, especially in dense concentrations, blocks light. See all those dark patches out here? That's where a lot of material is blocking our view. The whole Milky Way would be exceptionally bright, like this little window right here, if it weren't for all that gas and dust. But by blocking our view, we get to see that bright structure pop out ever so slightly more. Now, our Milky Way is very far away from us. If we wanted to see something that's far but still in our neighborhood, looks like we had a great suggestion from Sunil. We are going to go check out Pluto. Now, zooming out to Pluto is a pretty long trip. Were we to take our spacecraft speed, the speed of actually launching something out there, this would be a 10-year-long show. We haven't got time for that. We could travel at the speed of light, in which case it would only be about a 4.5-hour-long show, but we don't have time for that either. To get out to Pluto in a couple seconds, we are breaking many laws of physics, but it is worth the trip and worth the transgression. Check out these mountains. Now, these are sometimes called the penitents or the dragon's teeth. When you look at them, those blade-like parallel ridges, these are something weird, something truly exceptional. These are mountains made out of ice. That's kind of weird. Here on Earth, when we have a mountain, we expect it to be made of rock. Rock makes up the crust of our planet, so that makes perfect sense. When rock bumps into rock, often it forms a mountain range, either through subduction, which is one plate sliding beneath the other, or both of them bashing into each other and creating an uplifted mountain range. But on Pluto, there's a different form of mountain formation. We think some of these mountains are being carved by the sun. Now that's bizarre. But imagine, on the surface of Pluto, the outer surface is ice. The crust is ice. What you make mountains out of is ice. When sun shines on ice, it imparts some energy into it. And when that happens, it evaporates. Or at least that's what would happen here on Earth. It would go from a solid to a liquid. I guess that's melting. On Pluto, it doesn't melt. It sublimates. And sublimation is where you go from a solid straight to a gas. Do not pass liquid. Do not collect $200. That sublimation process means that it escapes the surface and becomes part of Pluto's thin atmosphere. Now, the mountains go straight from surface material into atmosphere. That's bizarre. We don't see that really happening here on Earth, except at the top of our very tallest mountains, like the Andes and the Himalayas. That's where sublimation can be seen here. Now, that's super cool, and it makes mountains completely different to the ones we're used to. We have other beautiful structures on the surface of Pluto, like these plains out here. These plains really give us a great insight into the temperatures on the surface of Pluto. This plain is like a slushy paste made of nitrogen. Nitrogen makes our atmosphere. It's so energetic here that it stays a gas even in our coldest temperatures. But on Pluto, it is so cold. How cold is it? It is so cold that the nitrogen that hovers around Pluto turns to this paste-like liquidy stuff on the surface. So that is a completely alien world to us humans. Juan wants to know if it's possible to visit a comet like 67P, Churyumov-Gerasimenko. That is potentially possible. We do have cometary stuff in the software, but I think like the view I tried to give you of our Milky Way, we took a lot of assets out of regular OpenSpace so that we would get it to look nice and smooth when we gave presentations. And I believe a lot of our comets were ones on the chopping block. But you can see comets, especially their orbits, and you can even show how comets move over time. That's an amazing view, but for some comets, you really got to give a lot of time forward, fast forward by a huge amount to get them to seem to move at all. Because a lot of the comets that travel around our sun travel at extreme distances, way out in space. And because of that, they don't move very quickly at all. Now, some of these things, these cometary objects, actually lie half the distance between us and our nearest neighbor stars. It's about 2 light years from Earth, but that would be the extreme outer edge of what's called the Oort cloud. And those are comets we've never actually seen. We can infer their presence based on the orbits of some objects that have passed nearby, but things way out there are so far, they don't bounce much light from our sun, so detecting them can be a huge challenge. What we're looking at here is not a comet, though. This is Uranus, actually. So looking at Uranus, you can see dark striped bits. That's clouds above the surface. You can also see light stripy bits, or at least you would if we didn't have nighttime on Uranus. Let's try this out. Turning off nighttime, it looks like a completely uniform bluish ball, but that's not the case. You can see some variation. Like I said, those white clouds, and if you move around enough, you get to see some darker clouds too. But you can also see a color variation. Here's one of those dark patches. Right up here, check out that yellowy region. If I go down to here, you can see a matched yellowy region at the other pole. Now, when we show our planet trails, this shows how objects travel around the sun. When I bring back our nighttime on Uranus, you can start to see which face is aiming towards the sun. Now, this is a really cool thing about Uranus. You can see how it travels around the sun, that line right there, pretty close to the ecliptic, the line where all of our planets are traveling, kind of like they're all moving on a nice flat plate. But let's check out that yellow region again. You'd expect it to be up here, right? At the North Pole or the South Pole? Well, it turns out the poles are very close to the direction of the sun. Now, that means that instead of spinning like a planet does, or our planet does through the solar system, it's more rolling through the solar system. And the pole is facing towards the sun. So challenge yourself. Imagine standing on the pole of Uranus. As the planet spins, what would you see the sun do? I always think that's a fascinating thing, to try and imagine the cycles we're familiar with, day and night, even annual cycles, the motion over the course of a year. What would it look like from a place that's not Earth? The answer is often very different than what we are used to. Okay, so backing out a bit, let's see if there's some other cool things I can show you. Any other suggestions from the audience are most definitely welcome. We had a request last week that I was unable to, or excuse me, 2 weeks ago at this point, Mary covered for me last week, of a planet very close to the sun that was requested right when the program ended. So in order to make up for that, I'd like to take us in to Mercury. Or at least what should be Mercury. Something weird is going on. Mercury's surface is normally gray, but normally covered with craters. Seems like my computer is having a rough time of it. So, once again, I'm deeply sorry to say we're not going to show you the surface of Mercury. We will get there eventually. Okay, what else would be good to check out? We are currently talking about some of our shows we're hoping to bring back for our programming block, especially for schools. And one of the conversations was focused on Titan. Titan is a super interesting world of our solar system, but not one of the major planets. For this, we're heading back out to Saturn. And when we do, you can see the surface of Titan as it would appear from underneath its clouds. Now, Titan's surface is normally impossible for us to see. When we send our radar through those clouds to bounce off the surface and come back, we get this image to show us where the radar bounced back smoothly, showing us a smooth surface, where it bounced back or was absorbed, often by a rough surface or something that is radar dark. Now, looking around there, you can see the light parts and the dark parts have a huge amount of interplay, especially around the equator. There seems to be some activity there. Now, again, this is a very cold world, like Pluto. Water would be as hard as rock, so it makes up some of that outer surface, but there is liquid on the surface here, and even more liquid than Pluto. This liquid would be more like rocket fuel here on Earth. Now, going from a chilly world like Titan, Cheryl's got a cool idea, or a really hot idea, I guess. Let's go check out the sun. Now, when we see the sun, you're going to see a brightish glow. If you've got exceptionally powerful eyes, you might be able to pick out a little tiny dot right at the middle of that glow. As we get closer and closer, you see the dot get larger and larger. This is what we would call the photosphere of the sun, the actual surface that makes the light we see. But the sun is sneaky. The sun is actually hiding several layers. When we imagine looking at the sun's just surface, by turning off that outside glare, we're actually getting rid of what you might call the corona of the sun, the outer wrapping. When we get rid of the chromosphere, that's the invisible to our eyes reddish layer wrapped around the outer surface. Looking even deeper though, that photosphere, you can see where light is being produced. Now this makes a huge amount of light. If you ever want to really get that experience, especially in these summer months when we've got a nice angle towards the sun, walk outside on one of these 104-degree days. Don't stay out too long. but feel that radiant light hitting your face and imagine that you're feeling energy that was released millions of miles away. Now, we say it's 8.5 light minutes. That is a huge distance. And that light has traveled all that time, all that distance, to bonk off your face and make you feel a little warmer. We had a question from Seth. We're talking about radar. Can we see that radar map of Venus? We absolutely can, Seth. Let's head out over Mercury, which is still not cooperating, to go see Venus. Now, when you look at Venus from above, you get to see that interesting color variation, yellows to dark browns, even some white. But these are the upper clouds. Just like Seth asked, if we want to see beneath those clouds, we use radar in much the same way we did for Titan. In fact, we did it on Venus first. If we wanted to see that, all we got to do is toggle off that atmosphere. We get some weird artifacts sometimes from the taller parts of Venus. Those should go away momentarily. As we do, it looks like someone is doing crop irrigation on the surface of Venus, but that I assure you is an artifact. Watering stuff on Venus would not work. We get to see that surface, and the reason why irrigating on Venus wouldn't work is because the temperature is much, much hotter than the surface of Earth. It's around 900 degrees on the Fahrenheit scale, and that means properly it's hot enough to melt lead. So water does not stand a chance. There we go. We're starting to get a little bit better resolution. As our better map is tiling in, you get to see some of those flow features, smooth plains where it looks like rock has moved across the surface, covering up damage and scarring from previous impacts or other eruptions. Venus is an active world. A few papers recently suggest there's more surface activity than previously thought, and that is an exciting idea. Because where there is energy, there's potential for life, or at least not on Venus, there would be potential for life. Venus is so acidic, such high pressure and such high temperature, we don't think that life would have even a chance of surviving there. But knowing that a planet the size of Venus has some subsurface activity, well, that's an exciting thing. Guillermo asks, how accurate are these orbits? Can you simulate eclipses or transits? Guillermo, boy, can you. When you're using OpenSpace, we often fudge the date so that a cool feature is looking towards the sun and is well illuminated, so we don't have to do a bunch of poking around in the back end to make stuff look right. Just by setting the date, we can make things look just the way they're supposed to. But I'll tell you what, we can show you the planet trails, which shows you the relative orbits of all these worlds. You can see some of the interesting features, like the significant dip and dive present in Mercury's orbit around the sun. When you're looking at that, that is actually what Mercury does. We discovered the relativistic distortion of space by observing some of the strange elliptical changes in the orbit of Mercury. But looking around here, you can see the positions of the planets. And let's think about that. Let's find our third planet from the sun. Earth is right there. So Venus should be in approximately the same direction as the sun, but maybe setting a little bit after the sun. Mars is pretty close to opposite the sun, so should be relatively visible. And out here, Jupiter and Saturn are also opposite the sun, so we should be getting a good view of them as well. And out here, you can even see Uranus is pretty close to the opposite direction, as well as Neptune. So you can quiz me next week, tomorrow. Tune into Bing's broadcast and see if those planets are actually in our night sky. I'm pretty sure they all are. Mercury would be a big challenge to spot from Earth, but the rest of them should be possible. And because of that, well, you can see that the orbital representations we have for our planets are accurate for a given time. If I bring back our little menu, you can see that as of Tuesday, the 25th August at 23 hours, 54 minutes, and 4 seconds GMT, Greenwich Mean Time, we should have the accurate representation of the positions of all the planets. If I decided I wanted to go forward a couple years, forward a couple years, we can see where the planets would be as of a specific date. It's a really fun way of controlling what parts of the universe we're seeing, not just in a spatial representation, but also a temporal, a time representation. You can jump forward or backwards, see eclipses, transits, all that cool stuff. And the size of the planets is accurate too, so you should get a pretty good and accurate representation of what eclipses or transits are visible. Okay, now we're zooming back from our solar system. You can see the glare of the sun there, and that tells us we are moving into interstellar space. That's about how bright the sun would be at this distance compared to our background stars. If we move back far enough, the sun just blends in, becomes one of the multitude of stars that exist around us. We spent a lot of time examining the planets that travel around our sun, but right now we are confronting in astronomy the very real notion that our solar system is anything but alone. Just like our sun is one of many stars, our solar system is one of many solar systems. These planetary systems around other stars are called exoplanets or extrasolar planets for long, but you can see them clustered in different parts of the sky. In some directions, we have a lot of them, in others, very few, but that, we think, has more to do with where human beings have looked than where there are actually planets. For example, this region is just completely stuffed with planets. There's just tons of them. Is that because there's more planets there than anywhere else? No, or at least probably not. What we can say with confidence is that is where the Kepler Space Telescope was looking for planets for 4 years, and oh boy, did it find a whole bunch. So we're pretty sure that anywhere you positioned a similarly sized field of view around our Milky Way, you would find a similar number of planets out there. That's really exciting. Based on all of our estimates, we can say with some degree of confidence, planets are just about as common as stars. In fact, they're probably more common than stars. Let's take our solar system for an example. How many stars do we have? 1. How many planets do we have? 8. To make the math easier, let's pretend there are only 5 planets. So for every 1 star, there's 5 planets. Let's think about our galaxy, that beautiful Milky Way we picked out before. If we're using the Milky Way as a good model for our galaxy, and every bit of counting we've done says that there should be around 4 billion suns that make up our galaxy. If that's the case, there's 4 billion suns and 5 planets per sun, then you come up with a shocking 2 trillion total solar systems out there. 4 times 5 is 20, add a 0. All of a sudden, we're looking at 2 trillion other planets around other stars. That's mind-blowing. I can't even hold on to that number in my head. Thinking about that gives me the willies. So when we talk about the idea of other planets, other solar systems, it's a really exciting thing and something we are still trying to wrap our heads around, confront, and learn more about. Now, I noticed one very strange thing as we flew back into Earth I wanted to point out because it's a really cool feature of OpenSpace. Notice something kind of funny with Earth? What's going on here? It looks like someone polished this part of Earth clean, and this part of Earth, well, that's all. We see clouds, we see Australia, we see relatively normal stuff. Alas, North America is gone. Should be right there. What's happening? Remember when I jumped forward in time? Every day we get a new picture of planet Earth from the Suomi spacecraft run by NASA and NOAA, and every day OpenSpace brings that into our computer so that we get to see Earth as accurately as possible. It's wonderful to be able to see Earth in this detail. It's a little sobering to see things like wildfires moving across the surface of Earth in not quite real time, but close to it. Well, it didn't have time to complete the photo for today, but you can see the last strip that was taken. We don't have a photo from the year 2024, so it shows us the last photo as of now, and that gives us this missing swath right here. Now, when you look at planet Earth in the OpenSpace software, you get that wonderfully up-to-date, super cool representation of how our planet is changing. That's a cool thing. One day, maybe we will have an understanding of these other planets and a degree approaching that of how well we know Earth. But Earth is our home. Earth is the planet we've spent the most time studying it, and fundamentally the one we know best. So it'll be a long time till then when we get to show you the surfaces of those other worlds and their changing weather in a software like OpenSpace. For now, I hope you can be content with our solar system and our own wonderful planet Earth. But with that, I think our tour has come to an end. I would like to thank all of you for tuning in today. I think we had a great back and forth. If you want to let us know how OpenSpace looks on your computer or how excited you are about it, just follow the link in our comments and let us know. This is a NASA project done in conjunction with the American Museum of Natural History in New York, and they would really appreciate you letting us know just what you think. So with that, thank you all for tuning in for our broadcast. We hope you stay home, stay happy, stay healthy, stay clear of any smoke you can this week. It's been a tough one for all of us here in California, but the Academy cannot wait until we get to open our doors again and see all of you in person. But for now, thank you for joining us. Have a wonderful rest of your